Hello friends, continuing with the chapter Electric Potential and Capacitance. Today we come to the second topic, equipotential surfaces. Previously we have learned about electric potential. In that we have talked of electric potential energy of two charge system, electric potential and electric potential difference. And now we go to the second topic of this chapter, equipotential surfaces. Equipotential surfaces. Now the definition of equipotential surfaces: the surfaces over each point of which the electric potential has a constant value. I repeat, the surfaces over each point of which the electric potential has a constant value. For example, number 1, family of concentric spheres S1 and S2 about point electric charge Q at center of spheres. 2, family of planes at right angle to the uniform electric field E. Here you can see in the diagram there are planes at right angle to the electric field E. So these family of planes all are equal potential surfaces, like spheres about a point electric charge. Example 3, equipotential surfaces due to an electric dipole are shown in this picture. So you can see how outside the dipole side the spacing between concentric spheres is increasing and inside it is decreasing. Example 4, equipotential surfaces due to two equal positive point electric charges separated by small distance are shown in this picture. And you mark the inner part. Here the spacing between spheres is increasing and outside it is decreasing, just the reverse of the above case. Now, salient features of equipotential surfaces. Number 1, no work is required to be done in moving any charge between 2 points on equipotential surface. That is, WAB is equal to 0. Now, since we know WAB is equal to Q naught into VB minus VA, and here VB is equal to VA on equipotential surface, therefore VB minus VA is 0, or WAB is equal to Q naught into 0 is equal to 0, or hence WAB is equal to 0. So you look at this diagram. This diagram is a equipotential surface. We have 2 points A and B. At A, electric potential is VA. At B, electric potential is VB. At VA is equal to VB. So therefore, when VA is equal to VB, then VB minus VA will be 0. So therefore, work done, WAB will be equal to Q naught into 0. That will be equal to 0. Hence, WAB is 0. Or we can say no work is required to be done in moving any charge between 2 points on equipotential surfaces. Now, electric field is equal to dV by dr and is always perpendicular to equipotential surface. Let us see how it is. Now, second feature of equipotential surface, magnitude of electric field intensity E is equal to dV by dr. Let us see how it comes out to be. Since line integral of electric field between 2 points is equal to potential difference between those 2 points. Mathematically, we have minus integral a to b E dot dr is equal to Vb minus Va, or we can write Vb minus Va as integration a to b dV, because Vb is more than Va, so we take the difference as Vb minus Va. Or small potential difference dV between 2 points separated by a small distance dr is given by the expression E dr equal to dV, or E is equal to dV by dr. So this is how we have electric field, magnitude of electric field E is equal to dV by dr. We call it as potential gradient also sometimes. Now, third feature of equipotential surface, direction of this electric field is always perpendicular to equipotential surface. I repeat, direction of electric field is always perpendicular to equipotential surface. Let us see how it is. Now, since we know line integral of electric field between 2 points is equal to potential difference between those 2 points, and mathematically expressed as minus integral a to b E dot dr is equal to Vb minus Va, because Vb is more than Va, so we take the difference as Vb minus Va. Or minus E dot r is equal to Vb minus Va. But Vb is equal to Va on equipotential surface. Therefore, Vb minus Va is 0. Or minus E dot r is equal to 0. Or magnitude of E and magnitude of r into cos theta is equal to 0. But E can't be 0, r also can't be 0. Therefore, cos theta between E and r must be 0. And it is possible only when theta is pi by 2. Now, if theta is pi by 2, then E must be perpendicular to r. But r lies on equipotential surface. Hence, E is perpendicular to equipotential surface, because E is perpendicular to r and r lies in the equipotential surface. Thus, we can say the direction of electric field is always perpendicular to equipotential surface. So, this is the third feature. We have learnt the salient features as number 1, work done in moving a charge on equipotential surface from one point to the other is always 0. Magnitude of electric field E is equal to dV by dr, and direction of E is perpendicular to equipotential surface always. Now, fourth salient feature of equipotential surface, closely spaced equipotential surfaces indicate strong field region and largely spaced indicate weak field region, like electric lines of force. I repeat, closely spaced equipotential surfaces indicate strong field region and largely spaced indicate weak field region. Okay, so is the fourth one. Now, advantages of mapping equipotential surfaces. Up to some extent, mapping of equipotential surfaces give us a visual picture of electric field intensity. Where equipotential surfaces are closely spaced, in that region field is strong, and where these are largely spaced, in that region field is weak. So, up to some extent, we can view the regions where electric field is strong, where electric field is weak, by looking at equipotential surfaces. Okay. Now, assignment 2.2. What are advantages of mapping equipotential surfaces? Question number 2. A test charge Q0 is moved from one point to another on equipotential surface. Calculate work done. Question number 3. Prove that direction of electric field is always perpendicular to equipotential surface. Question number 4. Draw equipotential surfaces due to number 1. A single isolated positive point electric charge. Number 2. Two equal positive point electric charges separated by a small distance. And number 3. Due to an electric dipole. Question number 5. 4 equipotential surfaces A, B, C and D are shown in the figure. Intimate whether work is done or not in moving a charge Q along paths 1, 2 and 3. Okay. So you try to answer this question on the basis of the text that you have learned. Question number 6. Two identical plane metallic surfaces A and B are kept parallel to each other in air separated by a distance of 1.0 centimeter as shown in diagram. Surface A is given a positive potential of 10 volt and the outer surface B is earthed. What is the magnitude and direction of electric field between points Y and Z? So what you have to do? Question number 1 is, what is the magnitude and direction of electric field between points Y and Z? Okay, so try to answer this question. So here the most important point is B is earthed like this. Okay, and then you try to solve this question. Now thank you so much. With this we finish the topic of equipotential surfaces. Next time we will start with the third topic of this chapter, electrical capacitance. Till then, goodbye and good luck.